This is section 4.4. We're going to be doing more modeling. Woohoo! Okay, so we're only going to do 5 problems today, but just in case this is still giving you a hard time with figuring out how to model these functions, then we're just going to go through these and hopefully give you some more tips and tricks for problem solving. Okay, this first problem says a wire of length L is cut into 2 pieces. The first is bent into an equilateral triangle, and the second is built into a rectangle with a length that's twice the width. We're going to express the total combined area as a function of x, where x is the perimeter of the triangle. So I see here it's supposed to be area as a function of x, so ultimately I'm looking to do this. Area is a function of x. If I want to express each area, the area of this triangle is going to be found by root 3 over 4s squared, and this is a formula that we will give you. The area of the rectangle is just going to be length times width. Okay, we're going to add those two up together, but express them as a function of x, where x is supposed to be the perimeter of the triangle. So this is giving us a hint already with how, in terms of what variables we want to use and how we want to set it up. Because if we go back to our first constraint here, it says a length of wire L is cut into 2 pieces. Don't get confused, this is just a constant. It'd be like me saying a length of, or a wire of length 10. They're just giving you it as looks like a variable, but it's not a variable, it's just a constant. So that means that's our constraint. The length of that wire is going to equal x plus, in terms of the whole piece of wire, let's say I have a length of L. If I cut away x, then that means the portion left over is going to be L minus x. So that's what I'm going to write this as. The total length is equal to x plus L minus x. Okay? Now x, one of those pieces represents the perimeter of that overall equilateral triangle. So I'm going to call this x. We're going to say that that's the piece that goes and wraps around to form that triangle. Because again, it says x is supposed to be the perimeter of the triangle. Okay? Alright, now, let me erase this. Now let's talk about trying to figure out the area of that triangle. So in terms of the perimeter, and the perimeter is x, well, there's 3 total parts that form the perimeter of that equilateral triangle, and each one is the same exact size. So if I wanted to express the s here in this function for just the area of the equilateral triangle, one of the side lengths is equal to x cut into 3 pieces, right? X over 3. So right away I can plug this in to the overall area of this entire piece of wire, I suppose, and say that the area of just the triangle is equal to root 3 over 4 times s squared, and s we're going to substitute in as x over 3 squared. Okay, so that's just the portion for this triangle. Now for the rectangle, they give me some information here. They say that the length is twice the width. Length is twice the width. So if I call that w for the width, then this length here is supposed to be 2 times that size, so 2w. Therefore, remember the total area, the perimeter of this shape is going to be L minus x. It's that leftover piece that's been bent into this rectangle. So L minus x, again this is the perimeter, is equal to 2w plus w times 2, or just the same thing, 2w plus w. Okay, that's all of the parts added up together are supposed to equal L minus x, that constant minus x. So L minus x equals 6w. Now I'm going to solve for w and isolate that w because the area of that rectangle is given by 2w times w, right? We're doing just length times width, so 2w times w, and I get 2w squared. And now I can substitute this in for w right into here. Okay? So if I do that, I end up with 2 times L minus x over 6 squared. Now, I have, in terms of the triangle here and the rectangle, I have both of these functions written in terms of x. Remember, this is just a constant, it's not really a variable. Okay? So, now I'm just going to put those together to express the entire area, right? If I wanted to combine both areas, I'm just going to add them together. So let me do that. Let me erase and put those together. So the area of the combined triangle and rectangle is equal to root 3 over 4 times x squared over 9. I'm just simplifying. Plus 2 times the length minus x squared divided by 36. Okay? Now I'm just going to simplify a little bit further, and I end up with root 3 over 36 x squared plus L minus x squared over 18. So this is the total area as a function of x. Okay, so to recap that problem, what I wanted to do was eventually write the area of both the triangle and the rectangle as a function of x. So I wanted to express each one of them separately, okay, and then I put them both together. I tried to get both of them in terms of just one variable x, and that's why we worked to try to solve for the side length here and the width so that I could get it in terms of x and then substitute that into our general expression for the area of a triangle and the area of a rectangle. Okay? Okay, in problem 2, it says the volume of a right cylinder is numerically 3 times the surface area. We're going to find the height as a function of the radius, and then we're going to do a second function where we find the radius as a function of height. So let's start with our constraint. They tell us that the volume is numerically 3 times the surface area. So volume is 3 times the surface area. So this isn't like your typical constraint, because it doesn't give you solid numbers everywhere, but this is still a constraint. We still have an equation that relates, our variables. Okay? Alright, so let's express volume. Well, volume of a cylinder is the area of the base. Area of your base is pi r squared multiplied by your height. So we end up with pi r squared h. That's going to equal 3 times the surface area, and we talked a little bit about surface area before. It's 2 circles plus the rectangle that forms that part that wraps around the circle. So we have pi r squared times 2, because we have 2 circles, plus the area of this rectangle is, the dimension here is still the height, wrapping around would be the circumference, so this is 2 pi r times h. And we'll give you the formula too, but I just wanted to refresh your geometry there. Okay, so we have pi r squared, h equals 6 pi r squared plus 6 pi r h. Now, in terms of, seeing variables here, we only have radius and we only have height. Those are the 2 variables that are written here. What this is asking us to do is to find the height as a function of the radius. In other words, solve for height. Okay? The second problem here just means solve for the radius. Okay, solve for r, solve for h. So let's work on solving first for h. Now, when we went into literal equations, we always try to isolate the h and bring the h's to the same side. So see how these two pieces of our equation have an h in it? Well, I'm just going to subtract that over to the other side and write that as pi r squared h minus 6 pi r h equals 6 pi r squared. Okay. Now I'm going to factor out this h so that I can get it alone eventually. So I have h on the outside times pi r squared minus 6 pi r. And now I can divide out that whole term here so that I have h now alone equaling 6 pi r squared over pi r squared minus 6 pi r. And now I can work on simplifying this. I noticed that in the denominator here I can pull out a pi r and write that as r minus 6 in the denominator. And in the numerator, I'm going to have factors that cancel. Pi's are going to cancel. This r is going to cancel one of those r's in the numerator. So I have left over h equals 6r over r minus 6. So there is an expression that gives me h in terms of r. So you can write that out as h of r equals 6r over r minus 6. So this is a function, height is a function of the radius. Now for part b here, the radius is supposed to be a function of the height. Now I can start back with this original expression or equation here and then solve for the r. But you know what I want to do? I'm going to take a shortcut and I'm just going to solve this for r. Okay? So putting it back in terms of what we just ended up with, h equals 6r over r minus 6. I want to work on isolating the r. So I see I have two r's here. First thing I need to do is get rid of that r in the denominator. These are going to cancel now, and I have r minus 6 times h equals 6r. I'm going to distribute here. We have hr minus 6h equals 6r. Now I'm going to get the r's to the same side, so I'm going to bring this r over here. And I'm going to write that as negative 6h equals 6r minus hr. And now I'm doing what I did before. I just factor out the r, so 6 minus h equals negative 6h on the other side. Divide now this entire term. So bring that out, divide it. So it's getting a little messy and crowded, but I have r equals negative 6h over 6 minus h. So if I want to write that in function notation, this is the radius in terms of h is equal to negative 6h over 6 minus h. Alright, in problem 3, we're not given a diagram, so I want to first read out this problem and then try to draw a diagram that will accompany this so I can visualize this a little bit better. So it says a line is drawn from the origin to a point xy in the first quadrant on the graph of y equals 1 over x. So this is one of our mother functions, and if it's the graph of 1 over x, then this point here is 1, 1. Okay? Not that that matters, but that's what that branch would look like if it's in the first quadrant. Now, you have a point from the origin to anywhere on the graph of 1 over x. So that point, let's call that xy, because that's what they asked us to call it, is a point in the, I think it's labeled P, right, from point P. Now, from this point, a line is drawn perpendicular to the x-axis, meaning it's going to be a vertical line drawn straight down from the point P. It meets the x-axis at the point B. So we have triangle OPB. Hopefully you're noticing that this is a right triangle. So we did our first job here, which was to diagram the situation. Now we're supposed to write the area of the triangle as a function of x. The area of the triangle as a function of x. Alright, so area of this triangle is going to be given by 1/2 base times height. Hopefully the easiest way for you to do this, and that you're recognizing this, would be to find this base here and this height right there and plug that into your function. Now let's express what this little horizontal piece is from O to B. Well, in the very beginning of the problem, they said that this expression, or this point, was determined by drawing a perpendicular line from point P to perpendicular to the x-axis. So this means that that point B has to have the coordinate x0, which now means that the distance here is x units long. So we already have the base of this, and that's just going to be x. Okay? Now we need to work on the height. That height here is going to be found by taking the y and subtracting your y coordinate here, the overall vertical change. So it's y minus 0, which is just y. Now the problem is, for the height, I don't want it in terms of y. I only want it as a function of x. So now I have to do some thinking, and this is going to be very similar to what we did yesterday in one of the notes problems. Now this y output is given from the function 1 over x, right? F of x, or y, equals 1 over x. So therefore, I know that this coordinate is x, comma, 1 over x. So now I just found y in terms of x. So y equals 1 over x, and now I can plug, now I can plug that in for the height here, 1 over x, and I have a of x the area in terms of x is equal to 1/2, whoa, sorry, 1/2 times x times 1 over x. Now simplifying this, since the x's are going to cancel, I end up with just 1/2. What this is telling me is that the area as a function of x ends up being 1/2. No matter what, no matter where you draw the point on the graph of 1 over x, even if I drew it here, the area of this triangle here is 1/2. So it's constant, but it is always 1/2. Okay, so for problems 4 and 5, you're more than welcome to just pause and try to work these out yourself. But it's very important that you understand how to do these because they'll both be, I think, assessed on a quiz and a test. So make sure you're comfortable with both of these problems, with the setup and drawing the picture as well. In number 4, I gave you the picture. I think in the quiz, we're not going to give you a picture. We're going to ask you to actually create it on your own. But anyway, it's a really basic distance equals rate times time problem. But it's very complicated because of all this information. So you want to try to read, digest it, draw your diagram, and make sure that it makes sense. So it says a man stands at a point, and that point is A, on the bank of a straight river that's 2 miles wide. So one of the things that you want to do when you're drawing this, obviously I already have the picture, but the fact that it's 2 miles wide gives you some information. This segment, I'll do it in red, this segment here is 2 miles wide, so this is 2, and it says to reach the point that he's trying to come, downstream at, point B, he first rows his boat to point P. So he's going across the river, point B, and, point P, and then he walks the remaining distance. So this is I guess the path that he travels, okay, from A to P and then P to B. We are supposed to, based on his speed, we were supposed to find a function that models the amount of time it takes for this trip. So you've got two different parts here. You've got the distance from A to P and the distance from P to B. You also have two different rates because he rows the boat at 2 miles an hour and he walks at 5 miles an hour. Okay, so 2 miles an hour for the rowing and 5 miles an hour for the walking. Now, I'm going to do both parts individually and then add it together to represent the total amount of time. So if I were to just try to write this function in terms of time only, I'm going to say that time is equal to the distance over the rate. Okay? I'm going to take the time that it takes him to get from A to P, and I'm also going to find the time that it takes him to get from P to B, point P to point B. Okay? Alright, so let's work on from A to P. So, from A to P, this is a distance that we can express because we have a triangle. That's something that you want to notice here is that you have a right triangle, and the distance, if from this point to this point is 7 miles, and he walks X amount of, miles, then this segment is going to be given by 7 minus X. So if we wanted to express the distance that he actually walks or rows his boat from A to P here, this overall distance, we are going to use Pythagorean Theorem, and the sum of this squared plus this squared is going to equal our distance squared. So from A to P, so the distance from A to P is given by 2 squared plus 7 minus X squared, but we need to take the square root of that. Okay, so this is the distance from A to P, and that's the square root of 4 plus 7 minus X squared. Alright, so now we have the distance from A to P, and we want to divide that by the rate that it takes him to get from A to P. So we already have the expression for the numerator. It's going to be 4 plus 7 minus X squared. And you're going to divide that by the rate that it takes him to row that boat. The rowing speed is 2 miles an hour. So we're going to divide that by 2. So right now we have the time here that it takes in terms of X. just to get from point A to point P. Now to get from P to B, we're going to do the same thing. The distance from point P to point B divided by the rate to get from point P to point B. Now the distance from point P to B is already given to you in this diagram. That distance is x. For the rate, they also tell you that here. He walks at a rate of 5 miles an hour, so you have x over 5. So if we put those two together, the total time it takes to get from point A to point P, and the total time it takes to get from point P to point B, we end up with the square root of 4 plus 7 minus x squared over 2 plus x over 5. Now, I can work on simplifying this if I want to. If I want to get a common denominator here, I can call that this now. Oops, plus 2x. And that would be my function in terms of the distance that he walks. Okay, I know this is already getting kind of super long here. I apologize, but this is a really important question that I want to make sure that you know how to set up, because you're going to see it on your homework and you might possibly see this on a quiz as well. So, a Norman window is in the shape of a rectangle surmounted by a semicircle. Yeah, I didn't know what a Norman window was either, but I just drew one out. And so it's a rectangle, and then on top of that is a semicircle. So there's something you already know about this semicircle in terms of its radius. If this is r, then this shape here has to have a length, the rectangle has a length of 2r. Okay? Anyways, the perimeter of the window is 40, so this is our constraint. The perimeter is 40 for the entire window. But we're supposed to express the area of the window as a function of the radius of the semicircle. So express area as a function of radius means we're going to do this, a of r. And if I were to express the area of this function, or of this window, I have a rectangle and I have a semicircle. And the area of that semicircle is going to be pi r squared cut in half because it's just half of a circle, plus, if I know that this length here is 2r, it's going to be the length times the width here. I don't know, let's call that x. So 2r times x. Let's put those together. So right away, the only variable that I need to get rid of here is that x. That needs to disappear because I want to have everything in terms of just the r. Alright, now, when you guys look back on this problem, you want to look at the perimeter of the window is 40. You want to look at your constraint. So you have perimeter equals 40. Now, if I express the perimeter of this, I need to go around this rectangle, like so. So I have x plus 2r plus x. It's going around here. And then this portion of your window is a semicircle, so it's just half of a circumference. So instead of 2 pi r, you're just going to do pi r. So that total perimeter is equal to 40. Now, like we said before, we want to get rid of this x, so I want to solve in terms of x. So I have 2x equals, and I'm going to move everything else over, so negative 2r minus pi r plus 40. Okay? Now, the reason why I'm leaving it as 2x, of course, I could divide all of this out and get it in terms of just a single x, but I noticed that on the other side, I have 2xr, right? I could rewrite that as 2xr. And if I just simplify here and substitute this entire thing for 2x, I save myself the trouble of dividing by 2 and then remultiplying it all back out by 2. This is not something you have to be able to see, but it does save you a little bit of time. So, like I said, instead of plugging in, or instead of just solving for x alone, and doing all this, dividing out all those terms, and then realizing that eventually I'm going to have to multiply x by 2 anyhow, I'm just going to substitute that whole thing in. So I have this a of r equaling pi r squared over 2 plus, like I said, 2 and the x are going to get simplified, or substituted in with this value here. So r times this entire expression, negative 2r minus pi r plus 40. Now I'm going to work on simplifying this a little bit more. So I have a of r equals pi r squared over 2 minus 2r squared. Whoa. Minus 2r squared minus pi r squared plus 40r. Okay, now simplifying even further, this is just the same term. I know it doesn't look like it, but these two terms here are the same, and so is this guy. So if I wanted to express this all and factor out that r squared, I have pi over 2 minus 2 minus pi r squared plus 40r. Okay, so just recognize that this is the same exact variable term, and then treat the coefficients out in front. If they're just like numbers, if that was just a 3 minus 2 minus 6, you would simplify that. You're doing the same thing here. So we have pi over 2 minus pi, so I have negative 1/2 pi minus 2r squared plus 40r. Alright, and this is your area as a function of r. Sorry that it took 27 minutes to do this. This is a new low for me. I apologize. Thanks for sticking in there. Hopefully this is making perfect sense for you. If not, let's talk it over tomorrow in class. Good job. Bye-bye.